Hi, folks. Today we're going to talk about topological equivalence. What does it mean for objects to be the same from a topological perspective? And so first, let's review our topological structures. At this point, we have two different topological structures. The first is topologies. And so a topology is just a framework for a set. It's a collection of unions and intersections which describes how a set is built. It's applied to a set, and sets can have a number of different topologies applied to them. This can be a continuous set, it can be just a bunch of disconnected points, but we can form topologies on just about any structure. Manifolds are a little different. And so a manifold is an object which locally looks like Euclidean space. And so it has a topological framework, but locally it looks like either a line or a plane or some form of Rn. Not all topological objects are manifolds, but all manifolds have to have a topology. And so that's the key difference between the two. But really, we're thinking about things which locally look nice and might not look nice in the bigger picture. When we're talking about topological equivalence, we're asking what makes objects similar enough that we can do math on them. And so the real power of a topology is the idea of topological equivalence. When we think about all of these topological structures, an important question becomes, when can we treat them as though they're the same? Generally, we have two types of equivalence. We have homotopy equivalence and homeomorphisms. And so homotopy is about stretching things, and homeomorphisms is about mapping using functions. We're going to start with homotopy because that's usually the easier one to understand. And so broadly speaking, two objects are considered to be homotopy equivalent if we can continuously deform one object into the other. And so by continuously deform, we mean that if we treated the objects like they were made of rubber, we can stretch or reshape one object into the other shape. Generally, all that matters is the number of holes that an object has. And we'll talk about this one a little bit later, but if we look at the structure of a coffee cup and the structure of a torus, well, we can deform the coffee cup until it is the same shape as the torus. I just bring the bottom up until we have some solid structure here, and then we can stretch that solid structure down until we have ourselves our torus. If something can be stretched into a single point, it is called contractible. In the case of the donut and the coffee cup, they are not contractible. We can turn one into the other, but we can't turn them both into a point. Let's start by just thinking about the example of letters. And so consider the following letters as though they're just shapes. And so the shape of the letter O, X, Y, B, and D. And we'll consider them as line segments if you'd like. The letters X and Y are homotopy equivalent. If you think about it, if you just took one of the legs of the X and you just pushed it in, you would get the shape of the Y. And so again, treating these as though they're malleable, like they're made out of silly putty or made out of rubber, we can stretch one of them into the other one. And in fact, we could say that both of these are contractible. If we think of the shape X, we could just push all four of the legs in until it were one giant rubbery blob in the center. Same with the letter Y. If we pushed all three of the legs in, we would end up getting it so that it's compressed down to a single point. The letters O and D, we could not do that with. And so O and D are homotopy equivalent because we could just kind of round out the corners on the D and we get the O. And so this idea of treating them as though they are rubber, a little bit malleable, we can say that these two shapes, the letter O and the letter D, are homotopy equivalent. O and D are not homotopy equivalent to X and Y. There's no way that we can stretch the letter O and get the letter X out of it. The letter O, when you stretch it out, it is always going to have a hole in the center. The letter D, no matter how you stretch it, is always going to have a hole in the center. X and Y, no matter how you stretch them, they're never going to have a hole. And so because O and D have a hole in the center, no amount of deformations will get rid of the hole. And B, it has two holes. And so there's no way that we can stretch that into O, D, X, or Y. No matter how you stretch the letter B, you're always going to have those two holes in it. One example we often think to is the idea of knots. And this gives us a way to understand the different types of knots that exist. And so a knot is a topological structure. It's a one manifold, which is a mapping of a circle to something that is usually more twisted up. Some knots can be untangled into simpler knots, and these are considered homotopy equivalent. And so if we look at this example on the right, if we start with this mess of a knot, and we can kind of follow how everything is tangled together, well, when we smooth it out, we can then see that there's this loop which is underneath this string. We can pull that one out, and then if we untangle that or unwrap it, we end up with this shape over here. And so this is showing how homotopy works. We can untangle a knot and get some different shaped knot. We say a prime knot is a knot which has been untangled as much as it can be. And these examples here are a number of prime knots. None of these are homotopy equivalent to one another. There's no way that we can untangle this knot further and get it to be a circle. There's no way that we can untangle this knot, which has 4 different crossings, and get one of these. This knot has 5 crossings in it. 1, 2, 3, 4, 5. There's no way to untangle this to get a simpler knot. And so when you're exploring knot theory, this idea of homotopy becomes an important one because we want to know, do we have the simplest shaped knot that we can get? And then the big example is the donut and the coffee cup. To a topologist, a coffee cup and a donut are the same thing. They have the same number of holes and one can be demorphed into the other. They have homotopy equivalence. And the joke is that this can make breakfast with a topologist a very difficult thing. Our other form of topological equivalence is homeomorphisms. And so homeomorphisms work a little bit differently than homotopy. And so a homeomorphism is a continuous mapping between two spaces, which can also be undone. And so it has some inverse. When we look at the example here, we can take values on this map and we can turn them into values on this map. We can create a function which goes from this shape to this shape. What we can't do is we can't take a nice continuous function that goes from this shape to this shape. And it's for the same reason. It all boils down to the number of holes that you have. And so in this case, we can't create a mapping from here to here. We can't take a mapping from here down to this one, which has a hole in the center. But we could take a mapping from this thing, which has one hole, to this thing, which has one hole. And so it's similar to homotopy, but with a few big differences. If you map to a point, you can't really undo it. And so when we think about contractible maps before, contractible isn't really a thing for homeomorphisms because you can map a whole bunch of points down to a single point, but you can't then take that single point and undo it in a nice, smooth way. Knots work differently as well, and shapes just aren't as rubbery. We'll see what we mean by that. In many cases, homeomorphisms are considered a stronger form of homotopy. And here's one example. Letters. Let's think of the letters X and Y. Before we said they have homotopy equivalence because you could just take one of the legs and stretch it up to a point, and then you'll have the letter Y. You can even rotate this bottom leg until it matches, and they would look exactly the same. Well, while they're homotopy equivalent, they are not homeomorphic. We can't take a continuous map from this function or from this shape to this shape. And the real issue is going to be at this crossing. We can map any of the legs to any of the legs over here, but at this particular point where we have four legs coming together, there's no way that we can map four legs coming to a single point to a place where three legs are coming together. And that's the key difference between homotopy and homeomorphisms. We can think of other legs and see where, or other letters and see how this applies. And so the letters D and O, before we said they're homotopy equivalent, well, they're also homeomorphic. One has corners, that's okay. We can still create some function which is going from the curve of the letter D to the curve of the circle. That's no problem. Key thing to look for is the number of holes, and they both have one hole, it's all good. When we think of the letters E, T, and Y, they are all homotopy equivalent because they're all contractible, but they are also homeomorphic. When we think of the previous example, the X and the Y, these were not, because at this point, there were four legs coming out of it, while this one only had three legs coming off of it. In this case, when we look at the E, the T, and the Y, they all have a point where there are three legs coming off of it. And so for the Y, it's at the center. For the T, it's at the top. And for the E, it's the center left. There are three legs coming out of it. The bends and corners we don't worry about, but the fact that they all have this point with three legs, well, all three of them have that. Everything else we can stretch however we need to. Yeah, when we look at the structures of these letters, they all have three legs coming from some central point. This gets into the idea of graph theory, which we'll talk about soon. And the idea that we can map the legs of E to the legs of T and to the legs of Y. And so these are all homeomorphic. Of course, E, T, and Y are not homeomorphic to the letters D and O because they have very different structures. Now let's consider knots. And so when we talked about knots before, we said that these prime knots were not homotopy equivalent because we couldn't stretch one knot into another knot. They are homeomorphic though. And the reason for that is if we think about any of these knots, they're really just this circle shape. And so if we take some point and we follow the point around the knot, eventually we're going to end back at our starting location. These are all just different versions of a circle. It's just a circle which has been tied into weird ways. And so all of these knots can be mapped to a circle. And the circle can then be mapped to any of these knots. And so all of these knots are homeomorphic to one another. Now, it is possible to find formulas for all of these things. Generally, we don't do it too often, but it can be done. Often we focus more on the question of whether a homeomorphism exists and are less interested in finding the formulas, but we can find the formulas. In this case, I found a homeomorphism from a square to a circle, and this is the formula for it, which takes the square and turns it into a circle. It's a bit of a complicated formula. I actually asked a friend for help on this one. And they did an admirable job. And so when we look at this, we can take any point on this square and we can show how we can stretch it into this circle using a homeomorphism. When we think of the Mobius strip and the cylinder, it's a similar idea. Question becomes, are they homotopy equivalent or homeomorphic? And in this case, they can both be stretched into a circle. And so they are homotopy equivalent. They are not homeomorphic though. It turns out we cannot create a mapping which is continuous from one of them to the other. Weird things start to happen on the topology. And if you think about it, the issue if you used a piece of paper to create both of them, the issue would be where you taped that piece of paper together. Essentially, along that point, if you were to have a topology showing what's happening along those points, the maps would not line up very nicely between the cylinder and the Mobius strip. And so they're homotopic, but they are not homeomorphic. Similar idea with the torus and a sphere. The torus and the sphere are not homotopy equivalent, and they are not homeomorphic either. The general rule of thumb for a pair of manifolds is it all boils down to how many holes they have. And so whether we're talking about homotopy or homeomorphisms, the number of holes will often determine whether or not they are equivalent topologically. Another example is the Earth. When we think of the Earth, well, we can think of a topology describing the surface of the Earth, and the atlas with all of the different maps of the Earth will tell us what things look like locally, but it will not actually tell us the shape of the Earth itself. And this is one of the benefits and drawbacks of topology. It's geometry without geometry. And so a sphere and a pear shape are homotopy equivalent and homeomorphic. To a topologist, they're the same. If you think of a book of atlases, which shows all of the different maps of the world, it will not really distinguish whether or not the Earth itself is shaped like a pear or shaped like a sphere. And, the Earth itself is not a perfect sphere. It's a little bit bumpy. And understanding those bumps can help us understand the structure of the Earth itself. So this is why we think of topology as a tool for modeling difficult to model objects in a way which can bypass geometry. If we are thinking of the shape of a tree and we want to actually do some math involving the shape of a tree, well, having a topology which describes the shape of that tree can be useful. Final thoughts. In general, we think of topological structures as being equivalent if we can either stretch one into another or find some mapping from one to the other. Depending on what we're doing, we might prefer one over the other. If we have two equivalent structures, then understanding how one works will tell us how the other works. And this becomes useful when we're dealing with just about anything in the real world. I mean, again, there are no perfect triangles, but there are a lot of triangle-shaped objects. When we're trying to understand the shapes that we are dealing with on the day-to-day basis, well, we're not going to be dealing with nice shapes, but we can approximate them using nice shapes. And understanding how nice shapes works can help us understand how the more complicated shapes work. That's really the benefit of topology. And so with that, I'll let you get to work exploring where you find topological equivalence in the real world. Good luck, folks.